For as long as humans have observed the stars, marked the passing of the seasons, and navigated our world, we have measured our universe. The ancients used clay tablets and etched rudimentary symbols into them, unaware they were laying the foundation for the language that would be used to decode the universe. What began as simply counting livestock and observing the passage of time evolved into the system that would become the global language spoken by all of mankind and would create the foundation for our perception of reality. Mathematics is something many of us are introduced to at a young age as part of our education. In school, we learn to solve problems by manipulating symbols and following rules, but we never stop to ask, how did these rules and symbols arise, and why have they stood the test of time? Before modern mathematics, people relied on geometry and intuitive reasoning to understand the world. They devised tables and step-by-step methods to solve complex problems without symbolic notation. Greek mathematicians like Euclid and Archimedes elevated math to a rigorous art of logical deduction, using geometric proofs to explore order and beauty. But in the 17th century, a revolutionary shift occurred, one that would forever change humanity's understanding of reality. John Wallis, born on December 3, 1616, in Ashford, Kent, England, was a pioneering mathematician and ordained clergyman with a lasting impact on mathematical thought. Educated initially in Latin at grammar school, he went on to study Greek, Hebrew, and logic at Martin Holbeach's school in Essex. Though he was largely self-taught in mathematics, Wallis's natural curiosity led him to study not only to memorize, but also to understand the deeper principles behind the math he analyzed. In 1642, with the English Civil War underway, Wallis made his first attempt at code-breaking an encrypted message. He successfully deciphered a coded message within 2 hours. His aptitude for code-breaking quickly earned him recognition, and he went on to work as a cryptographer for Oliver Cromwell's intelligence service. This experience deepened Wallis's appreciation for the power of using symbols to solve complex problems, which would later influence his approach to mathematics. In 1649, Parliament appointed Wallis to the prestigious position of Savilian Professor of Geometry at Oxford as a recognition of his code-breaking contributions. A year later, he was appointed Keeper of the Archives, or Custos Archivorum, for the university. Wallis kept these positions for over 45 years, until his death. During this time, he elevated Oxford's mathematics collection to be one of the strongest in the field. The university press published many influential works in mathematics and science, including Isaac Newton's Principia. By the end of his career, Wallis was surrounded by the era's greatest mathematical works, allowing him to weave together the pieces of a vast, intricate puzzle that we call mathematics. Algebra is a language of symbols, using letters and signs to represent numbers and relationships, allowing us to navigate the unseen structures of the world. Each symbol, whether X, Y, or Z, is more than a mere placeholder. It stands for possibilities, unknowns, and patterns that can be discovered and manipulated. Through symbolic manipulation, algebra allows mankind to solve complex real-world problems, from calculating planetary orbits to designing deep-sea submersibles. It sets itself apart from geometry by dealing with quantities that are not geometric. Algebra opens up a vast range of applications, enabling us to work with abstract quantities beyond visual representation. Its symbolic nature begins with counting and evolves into basic operations such as addition, subtraction, multiplication, and division. More advanced algebra contains more complex operations, such as powers and roots. This layered structure of operations gives it a flexibility that allows it to tackle a wide array of problems and making it essential in both theory and real-world applications. Prior to John Wallis, mathematical expressions were often described in words that lacked a specific symbolic representation for a variable. For example, x cubed plus 6x equals 20 would be described as the cube plus 6 is equal to 20. The words implied the same variable for each term, which would pose a problem if the equation were in terms of more than one variable. Along with this, the concept of negative numbers was also met with skepticism. Early mathematicians dismissed them as absurd or fictitious. However, Wallis saw them as having a place in mathematics. He brought them into the number system by introducing something that is now taught as the foundation of our understanding of mathematics: the number line. A simple yet powerful idea, the number line created a bridge between geometry and algebra, a line stretching infinitely in both directions, with consecutive integers marked and ratios filling the spaces between. Wallis took these ratios and developed a standard notation for them. Where one might have once written the midpoint between 1 and 2 as 3:2, calling it the ratio of 3 to 2. Wallis introduced the notation we use today, 1.5. Besides accepting the negative number as a number and employing the streamlined decimal notation, Wallis also went on to adopt Harriot's notation for greater than, less than, and the plus and minus signs. He also introduced the infinity symbol for representing infinity. Where Wallis began to differ from Harriot was arguably his greatest achievement. Moving away from Harriot's method of notating a power by repeating the unknown variable, Wallis adopted Descartes' superscript notation to represent powers, using x to the 1, x to the 2, x to the 3, and so on. Moreover, Wallis unified various algebraic operations under a consistent framework. He redefined the square root as x to the 1/2 and represented reciprocals such as 1 over x as x to the -1, thereby incorporating roots and negative exponents into the broader structure of powers. These changes effectively create a new rule of algebra where x to the a times x to the b is equal to x to the a plus b for any real values of a and b. By consolidating these ideas, Wallis not only advanced algebra but also laid the groundwork for future developments in mathematics. The development of calculus is often seen as one of the most pivotal moments in mathematical history, with much of the spotlight falling on Isaac Newton and Gottfried Wilhelm Leibniz. However, John Wallis, often overlooked in this story, set the foundation for their groundbreaking theories. His contributions to algebra provided the essential groundwork upon which both Newton and Leibniz built their ideas. Newton, who was 26 years Wallis's junior, drew inspiration from Wallis during his early academic journey. Historians note that Wallis was one of the few mathematicians that Newton cited repeatedly in his Principia Mathematica. As for Leibniz, he too held Wallis in high regard. Their correspondence spanned several years, discussing mathematics, philosophy, and even theology. Wallis's approach to infinite series, transcendent curves, and symbolic representation found its way into Leibniz's works on calculus and logic. Leibniz even publicly defended Wallis's theological arguments, showcasing a deep respect for his intellectual breadth. Newton and Leibniz recognized the giants who came before them. Wallis's work was indispensable to the very foundations of calculus. They saw Wallace not as a rival, but as a mentor and an ally, frequently citing his methods in developing calculus and analyzing the structure of equations. John Wallis may not have achieved the same level of fame as Newton or Leibniz, but his contributions were foundational, his legacy enduring. Through his innovation in symbolic notation and his exploration of infinite series, Wallis provided the essential language and concepts that would define a new era in mathematics. In any good story, there's an antagonist, a nemesis who challenges the hero. In the story of John Wallis, that role was played by Thomas Hobbes. Their battles centered on the nature of mathematics, and Hobbes had a particular disdain for Wallis's symbolic approach to algebra. When it came to Wallis's conic sections, an acclaimed work where Wallis translated the geometric representation of conic sections into algebraic equations, he complained that it was covered over with the scab of symbols. Finding the mathematical notation so distasteful, he admitted he had no patience to examine whether it were well or ill demonstrated. Wallis saw the need to confront Hobbes head-on. In an era without scientific journals to regulate discourse, public debates like these carried weight. Wallis felt compelled to address Hobbes's criticism. In the end, Wallis exposed Hobbes's limited mathematical abilities, firmly establishing his own expertise. And yet, while Wallis successfully defended his work, these prolonged disputes with Hobbes came at a cost. The feud overshadowed Wallis's contributions and fed misleading narratives that detracted from his achievements. Today, historians agree that the rivalry, though memorable, was a distraction that unfairly colored Wallis's legacy. With a mind unrestrained by convention, Wallis redefined the mathematical landscape, bridging ancient geometry and modern algebra in ways that would shape the path of discovery for centuries. His algebra, his groundbreaking methods, his endless curiosity, each became a stepping stone for those who would follow. Newton and Leibniz may have brought calculus to the world, but Wallis laid the foundation, a foundation so profound that even today it stands as a testament to his genius. Centuries have passed, but Wallis's influence endures, casting a shadow as vast and unbounded as the universe he sought to understand. A legacy that, like the infinite itself, will never truly